In this lecture, we're going to talk about an important class of signals known as sinusoidal signals. And I'm going to begin by explaining why we're interested in sinusoids and what they are. Then we'll look a little bit at the notion of frequency, which is inherent to the notion of sinusoids, a couple examples, and conclude with a discussion of non-uniqueness, particularly for discrete-time sinusoids. If continuous time sinusoids have different frequencies, they're always distinct, but that's not the case for discrete time sinusoids. So why should we look at sinusoids? Well, they occur quite frequently in nature. For example, if we look at electromagnetic waves, such as the wave associated with light of a given color, or the wave associated with a microwave signal, those waves are sinusoidal in nature. And if I look at physics, where I have oscillatory motion, such as due to the position of a pendulum, or if I take a mass and hang it from a spring and have it bounce up and down, or perhaps when your shocks are really bad in your car, you end up with sinusoidal motion. But more than that, it turns out that we can describe almost any physical signal as a weighted sum of sinusoids. And this turns out to be a very, very powerful property that gets used a lot in signal processing. Lastly, the notion of frequency is part of our everyday experience, especially when we talk about sound. We talk about high frequency sounds, low frequency sounds, about boosting the bass, which is inherently a frequency notion. So sinusoids, it turns out, play a pretty important role. And I'm going to start by looking at a continuous time sinusoid. And we can define that mathematically as a function x of t, where the independent variable t is time, is equal to a cosine of omega naught t plus phi. If I take a graph of this, what we see is that the amplitude varies between plus a and minus a, and at t equals 0, we cross through an amplitude of a cosine phi, which of course happens because this omega naught t term drops out there. This is a periodic signal. This cosine repeats, and it repeats, say, every t naught, as I've illustrated down here at the bottom. We'll call a the amplitude. Phi we'll call the phase shift of the sinusoid, and omega naught is the frequency of the sinusoid. There's a relationship between the period, t naught, and the frequency, omega naught. That is, as the frequency goes up, the period's going to go down, and vice versa. We have a discrete time sinusoid written as x of a function of n, which we're going to assume is evaluated at integer values. It's going to be a cosine of capital omega naught n plus phi. Now generally I'm going to use capital symbols, omega capitalized here, to denote discrete time frequency, and we'll have lowercase omega to denote continuous time frequency. If we sketch this waveform, we see that it's a series of stems having a sinusoidal shape to them. And again, as in the continuous time case, the amplitude varies between plus a and minus a, and at n equals 0, I get an amplitude of a cosine of phi. And this also looks periodic, and if the period here will denote as capital N samples. So again, a represents the amplitude of the sinusoid, phi is the phase shift, and capital omega naught is the frequency. And the period n can be related to the frequency via this inverse relationship. Now, since n it has to be an integer, it turns out that puts certain restrictions on the frequencies of discrete time sinusoids that are, mathematically speaking, truly periodic. That is, omega naught has to involve a pi, so it can cancel this one and we can get ourselves an integer number. So frequency is inversely related to the period. And since we measure period in seconds for continuous time waveforms or samples for discrete time waveforms, we can measure frequency in terms of cycles per unit time, or since cycles can be measured in radians going around a circle, we can also measure it in radians per unit time. If I have a period of t naught seconds, that's going to mean that I go through one cycle every t naught second, and therefore my frequency is f naught equals 1 over t naught cycles per second. Now cycles per second is what we define to be the units of hertz. Similarly, in discrete time, if I have n samples in a period, that would imply I go through one cycle of my sinusoid in n samples, and I'd have a frequency f0 of cycles per sample. Now, this form of frequency is not usually used in discrete time. I've included it here for completeness. But normally, in discrete time especially, we look at radian frequency. Okay, so we use the fact that there's 2 pi radians in one cycle around a circle, and that leads us to radian frequency, capital omega naught, which is 2 pi times the cycle frequency, or 2 pi over n radians per sample. In discrete time, samples are considered usually unitless, so the units on discrete time frequency are often referred to as just radians. Radian frequency in continuous time is 2 pi times the cycle frequency, or 2 pi over t naught radians per second. It's important and useful to relate frequency in continuous time sinusoids and discrete time sinusoids. And we can do that using the notion of sampling. And after all, when we process any kind of data in a computer, we're going to sample it first. So if I'm interested in how a particular frequency in a continuous time signal, sinusoid, corresponds to a frequency in a discrete time sinusoid, sampling is the key for that. So we'll define a discrete time sinusoid, and we're going to define that discrete time sinusoid to be equal to the continuous time sinusoid sampled at intervals of n times capital T. So on the left, I've got my discrete time sinusoid. On the right, I've got my sampled continuous time sinusoid. And if I just do a little rearranging here, I see that I can write this in a form that looks very much like the discrete time sinusoid. And if I make a correspondence between capital omega and little omega times capital T, I can see that these are identical signals. So that leads us to this relationship between continuous time and discrete time frequency. And this is an important relationship. So discrete time frequency, capital omega, is equal to continuous time frequency, lowercase omega, times the sampling interval that's used to convert from continuous to discrete time. We can check this out with respect to units. Remember, capital omega was in units of radians, and if I take lowercase omega, which is in units of radians per second, multiply by seconds, I get the right answer. Now I can also relate discrete time frequency in radians to continuous time frequency in hertz or cycles per second, as I've shown over here on the right. And again, the units all check out. The cycles cancel, the seconds cancel, and we're left with radians on both sides of the equation. So I'm going to do a couple examples of sinusoids here and their roles, and we're going to use sinusoids of different frequencies to simulate musical notes. Now in Western music, we have 12 notes per octave. So that'd be like A sharp, B, C, C sharp, D, D sharp, and so on. So there's 12 of those in an octave, and an octave means that the frequency doubles. So it turns out that the frequencies between all these notes are spaced by multiples of 2 raised to the 1/12. Now, a major scale doesn't have every possible note in it, but it goes through in a particular order. But knowing the notes that are in the scale, we can determine their frequencies. So it turns out that C has a frequency of 523.28 hertz. And if I wanted an octave above that, I would double the frequency. If I wanted an octave below that, I would cut the frequency in half. But using this starting point, we can calculate all the frequencies of the rest of the notes in the C major scale, as I've listed here. So what I'm going to do in my demonstration in a moment is we're going to look at using sinusoids of these frequencies to play the C major scale. Then we're going to show an illustration of approximating an arbitrary waveform as a sum of sinusoids of different frequencies. And we'll do that using a saxophone playing the note A. So in this figure, on the top panel, I'm showing 1 second length notes going through the C major scale. So this is C, D, E, F, G, A, B, C. Now, because of the time scale and the relative frequencies of these notes, you can't see the sinusoidal oscillations in here. It just looks solid. So that's one thing about this graph. The other thing is that I decided to taper the notes down in amplitude at the end and gradually start them when I went to the next note. So I introduced this taper artificially. We can blow up sections of these notes, and I've done that in the bottom two panels. So the middle panel contains an expanded version of the note C, which is at 523.28 Hertz, showing 20 milliseconds of that note. And you can see that it's a sinusoid with a certain frequency. Then in the bottom panel, I blew up the note A, which is right in the 5 to 6 second range, again showing 20 milliseconds of the note A, which has frequency 880 Hertz. And you can see a clear difference between the sinusoid frequency or period for the note C and the period for the note A. So I'm going to play now the C major scale through MATLAB. So let's do that again. And so it starts with C, D, E, F, G, A, B, C. So that's the regular C major scale. And that doesn't really sound like any particular instrument because those are just pure sinusoids. Now, instruments have typically a bit more complicated waveforms, and we can see that by looking at a recording of a saxophone. So this, again, in the top panel, this is showing the waveform associated with a saxophone playing the note A, a little over 20 milliseconds. Okay, so you see that it does look periodic, is a repeating structure, but it has lots of complicated wiggles in it, and that's what gives the sound its particular quality, that we know it's from a saxophone as opposed to being from a guitar. Now, I said that we could represent arbitrary signals as sums of sinusoids, and we're going to explore that now. We'll learn later how to pick the amplitude and phases of the sinusoids so that when we add them up, we get this, but for now I'm just going to illustrate it. So the first component has the same frequency or period as the note that I'm trying to approximate. And you'll note that the phase is chosen so that the peak is approximately lined up with the peak of the saxophone, and the negative dip on the sinusoid is approximately lined up with the minimum of the saxophone note. So you can see that this saxophone note probably has an oscillation that looks like the sinusoid embedded in it. Okay, now we're going to start adding additional terms of higher frequencies. So here in the top panel is the original sinusoid that we started with. Then we're going to add a component at twice the frequency. It turns out then I get this distorted version of the sinusoid. I have a little steeper section here. It's much steeper going down the back side, and it's a little flatter in coming up from the minimum. Okay, so that's what I get with two components. If I add a third component in, as shown in this middle panel, then I get a bit more complicated looking signal. I've sharpened up this peak. I've introduced a plateau here and put another dip down here, just by the way that these oscillations in this sinusoid combine with my existing signal. Okay, so that's with three components. And we're going to add a couple more, and I'm just going to skip ahead in the visualization here. So this is what we end up in the top panel after 6 components. Okay, that's 6 sinusoids. And if we add in the 7th one, what you see that the 7th one does is it tends to flatten out the peak a little bit, and also flattens out this plateau a bit, and the other effects are not as visible. So we're going to go to the 8th component, and this 8th component adds a little bit of the detail back into this peak and gives a little more subtle character in the positive peak here. I'm going to stop at this point and compare this waveform to the original saxophone waveform. So in the top panel, I have the saxophone as it was recorded. In the bottom panel, I have the effect of approximating this with 8 sinusoids of different frequencies. And you can see it looks pretty similar. Now, the differences are pretty subtle, but in this plateau region here, they look just slightly different. And it's hard for me to see differences elsewhere. So using 8 sinusoids, I've done a very good job of approximating the original signal of the saxophone, and if we listen to these two, you can hardly tell the difference. In fact, I can't tell the difference. So first I'm going to play the recorded saxophone playing the note A. Now I'm going to play my approximation using these 8 sinusoids. Hard to tell the difference. Let's listen to them once more. The original, and then the approximation. So this ability of being able to approximate arbitrary signals using combinations of sinusoids with different frequencies turns out to be incredibly powerful, and it's a concept we're going to use repeatedly. Now, I mentioned at the start that there was this issue of uniqueness with discrete time sinusoids that doesn't occur in continuous time. In fact, with a continuous time sinusoid, if you have two sinusoids with different frequencies, the sinusoids are guaranteed to be different. Okay, if omega 1 is not equal to omega 2, then sine of omega 1t will not be equal to sine of omega 2t. That's true whether this is a cosine as well. However, the situation is different in discrete time. Because we're evaluating discrete time sinusoids at these integer indices, it turns out that if you shift the frequency by some integer multiple of 2 pi, where I'm assuming m is an integer here, you end up with the identical sinusoid. We can express that mathematically by saying that if a frequency omega 2 is equal to a discrete time frequency omega 1 plus an integer multiple of 2 pi, then sine of omega 1 times n is identically equal to sine of omega 2 times n. This is easy to show using trig identities. So what I have here on the left is I've expressed sine of omega 2n by replacing omega 2 with omega 1 times m 2 pi. This is just a sum of angles, so we can use the sum of angles formula for a sinusoid to write the left-hand side as sine of omega 1n times cosine of m 2 pi n plus cosine of omega 1n times sine m 2 pi n. Now this simplifies because of the fact that m and n are both integers. Then this argument inside the cosine and the argument inside the sine function are always integer multiples of 2 pi. Well, we know that the cosine of any integer multiple of 2 pi is 1, so this cosine is going to disappear. And we also know that the sine of any integer multiple of 2 pi is exactly 0. So that's going to wipe out this second term, and we're just left with sine omega 1n. Now I have an example to demonstrate this in MATLAB, and we're going to compare two continuous time sinusoids and two discrete time sinusoids where the frequencies of each sinusoid are shifted by 2 pi. So what I'm showing here in the top panel are the two continuous time sinusoids. The blue curve is for a sinusoid that has frequency pi over 5, and the green curve is for a sinusoid that has frequency 11 pi over 5. 2 pi plus pi over 5 gives you 11 pi over 5. And you can clearly see that these two sinusoids are distinct. Now in the middle panel, I'm showing the discrete time sinusoid cosine pi over 5n. In the bottom panel, I'm showing the discrete time sinusoid cosine 11 pi over 5 times n. Now these two discrete time sinusoids are identical. You can see that by looking at the two plots. Now it turns out that the explanation for this lies in the fact that the discrete time sinusoids are only being evaluated on the integers. So if I go back to my two continuous time sinusoids, the only difference here is that here I'm evaluating in continuous time, I'm evaluating t on a continuum. Here I'm evaluating n on integers. So if we look at the continuous time sinusoids, whenever there's an integer index, so t or n is equal to 4, these two sinusoids have the exact same value, and that's what we see down here. At 5, again, the exact same value. So at every integer, or the two continuous time sinusoids intersect, and that gives you the exact same value for the discrete time sinusoids. So we'll wrap this up by reminding you that these sinusoidal signals are very common in nature and intuitive in our experience, and they also turn out to be very useful for signal processing. We've seen that the frequency of a sinusoid is inversely related to its period, and that if I have a discrete time sinusoid and a continuous time sinusoid, the frequencies of the discrete and continuous time sinusoids are related through the sampling interval that is used to convert the continuous time sinusoid to a discrete time sinusoid. that the discrete time frequency capital omega is equal to the continuous time frequency lowercase omega times the sampling interval t. And then lastly, we looked at how discrete time sinusoids are only unique over a 2 pi interval of frequency. So if I take any frequency and I shift it by 2 pi, I get exactly the same sinusoid. The frequency that we need to be concerned with, say, lies between 0 and 2 pi, because anything outside of this interval is going to produce an equivalent sinusoid to one in the interval.